My name's Matt. I work at Oxygen Forensics. I'll just give a very quick little bit of my background. So I've been at Oxygen for about 2 years. Before that, I did digital forensics as a practitioner in the UK military and then the UK government agencies, mainly with a focus on mobile forensics. But I've done computer forensics, drone forensics, a lot of sort of different types of digital forensics in the past. So the topic of today's webinar is quite specific. We're talking about two extraction methods that we have in Oxygen Forensic Detective. It will be quite technical as well, because I want to go quite deep into how these extraction methods work in our tool. One of the things that I always say at the start of these webinars is, forensics is very much a toolbox industry. I think most people have at least 2 or 3 or maybe even 5, 10 different tools. And I was very much the same when I did digital forensics as a practitioner. I was quite fortunate in the team that I was in that we had access to pretty much all of the digital forensics tools. For me, extractions with Oxygen, there were a few different methods that I would have used Oxygen for the most. Some tools are better at different things. We're not the best at iOS. We're maybe not the best at some other things. But actually, I think MediaTek and Unisoc devices are two devices that I would use Oxygen quite heavily for. So I want to go more in detail on those in our product. So the agenda for today, I'm going to talk about what are Unisoc or Spreadtrum as they used to be called, and MediaTek. Why are they important, and the extraction methodology, and the ways that we can extract data from them, and then go into a little bit more detail in the extraction methodology, talking about things like download mode, the way that we can do offline password recovery, and also a little bit about how you could request support for new devices with these chipsets if you have a detective license. So just in case not everybody has seen the device extractor in Detective before, or maybe people have Detective but they don't use it for extractions all that much. This is what the device extractor in Detective looks like. And I am going to be talking about the two methods that you see highlighted here. So the first one is Unisoc Android, and the second one is MediaTek Android. And this is all Android devices that I'm talking about. You don't find these chipsets in iOS devices. So talking about these two particular methods within the device extractor. So the first thing really that I want to talk about, what are Unisoc and MediaTek, and to make it as simple as possible, they are just silicon makers. They specialize in making chipsets, also known as SoCs or system on chips, and they make those for phones. They make them for smartphones. They also make them for feature phones or dumb phones, and a bunch of other things as well. You can find Unisoc and MediaTek chipsets in embedded IoT devices, infotainment systems in cars, and things like that. Today, we're really going to focus on smartphones. I will touch just a little bit on feature phones and dumb phones, because we do support feature phones for MediaTek as well. And actually, one of the upcoming releases will add support for Unisoc feature phones, but it's not quite in the tool yet. It will be in the next few months. Both of these chipsets do have a lower price point, which means that they're common in the the more budget devices, not necessarily older devices, but not the flagship Samsungs or Xiaomi's, etc., the more kind of budget versions of those vendors' phones. Although in recent years, MediaTek in particular, we've seen them move into some of the mid-tier devices. And if you take MediaTek alone, but certainly if you take MediaTek with Unisoc, they are actually the biggest chipset maker for Android devices. In fact, in the entire world, in the global market, they are just the biggest chipset makers for smartphones, full stop. Now, obviously, that will vary from country to country. Some countries will have more of these cheaper devices than other countries, but we do see them in every single country in the world. So I did a bit of online research. This is not my research. This is, a graph that I took from the internet, but I think it is accurate. The market share for MediaTek, and actually this graph only goes up to 2023, but it will be very similar for 2024, is about one third, 33, 34% for the global smartphone chipset market share. And actually, this graph also includes Apple chipsets. So if you take Apple out of that, then the MediaTek market share probably goes up quite a bit. And then we also have Unisoc down here in the purple. And I'm going to talk a little bit more about Unisoc's market share because it is quite an interesting one. So if I go on to the next slide, Unisoc used to be called, if you went back sort of 5 years or more, they used to be called Spreadtrum, and then they were bought by a company called Unisoc. I remember when I first started to do digital forensics, and it was quite a long time ago, more than 15 years ago. And I started to do that kind of work in places like Afghanistan initially. We saw a lot of feature phones and a few Androids, not very many back then, but pretty much all of the feature phones, if they weren't the really old Nokias, they would be MediaTek or Spreadtrum feature phones. And the market share between MediaTek and Spreadtrum, if you went back, 10, 15 years, it was always 95% MediaTek and maybe 5% Spreadtrum. What I did see that was quite interesting, when Spreadtrum were bought by Unisoc, which I think was around 2018, 2019, I can't remember exactly when it was, the market share for those chipsets went really high compared to what it was before. And we did see some of the major OEMs, people like Nokia, Motorola, they moved their cheaper devices from MediaTek chipsets over to Unisoc chipsets. And Nokia even did it for their feature phones as well. So if you bought a cheaper Nokia or Motorola, 5 years ago, it was probably MediaTek, but today, probably the majority of them are actually Unisoc. And the tool support for Unisoc has always been quite poor. I always struggled, if we went back a few years, to get extractions from Unisoc devices, which is one of the reasons that I like to talk about it, because we have really, really good support in Oxygen now. I did a bit of an exercise, actually. I went on the MediaMarkt website. I think this was actually the German one that I have on the graph here, but I've done the same thing for equivalent shops in the UK and the US and Poland and a few other countries, and it's always the same. If you look at the devices between 100 and 175 euros, the new devices at that price point, it's almost a 50-50 split between MediaTek and Unisoc chipsets. And actually, I've started to see slightly more Unisoc devices at that price point. So they are quite common at that price point. So a little bit of theory just before we go any further. I've talked about system on a chip or a chipset. What actually is that? On the left here, we have a very crude, basic diagram of a mobile device that I made. And the mobile device, the heart of it is this chipset. It will have other things. A mobile device will have some storage, like an eMMC or a UFS chip that has your 128, 256 gigabytes of storage or whatever it is. There will be some RAM, and there will be a bunch of other stuff like peripherals, like a keypad or buttons or a screen or a microphone, etc., etc. But the chipset is really the heart of the device, because if you open up the chipset and look at what's inside that single chip, there will be a number of other components that traditionally would have been separate chips, but now they are just contained in a single package. So it is things like the CPU. There'll probably be some modems in there now, maybe a GPU. There will also be a little bit of RAM and ROM, and the ROM that we find on the chipset is quite important, and I'll talk about that more. And then there could be, many other different things as well. There could be eFuses, which is something else that I'll talk a little bit about, all contained on a single chip. So this is actually a diagram that I found of a Qualcomm chip, but it just demonstrates what a chipset is in a little bit of a better picture. So you have this single chip with a number of different sort of distinct areas for different packages inside that chip. And before I go any further, I'd also like to just, because I haven't really talked about what these methods in Detective can do yet. Generally, what we do with these methods in Detective is we do a physical extraction, and for some reason the screen has just gone blank. I'm not sure why. Nor, are you still there? Can you still hear me? There we go. Okay, bit of a glitch. So normally we do a physical extraction, we do hardware key extraction, and then we do offline decryption. So it's a little bit of a different approach to some of the other tools that you might use, where the password recovery for locked devices happens actually on the device. In Detective, it's generally the case that we do offline decryption, and that allows us to do password recovery through things like brute force attacks or dictionary attacks. For the devices that are supported that are running full disk encryption and secure start, or devices running file-based encryption. Generally, those two types of devices, and file-based encryption is going to be the majority of new devices, pretty much all of the new devices. You can get that physical extraction or full file system, and also do the password recovery through dictionary attack or brute force. One of the interesting recent updates to the Unisoc and MediaTek methods, and something that I don't really have time to talk about, is that you also get offline key store decryption, which is a little bit different to doing live operating system level key store extraction. And it's really cool because you get all of the key store keys in decrypted format. So even if an app isn't supported, you will be able to go and decrypt it manually, potentially. But I don't have time to go into the key store stuff in too much detail in this presentation. Oh, apologies, went the wrong way. So the first one that I'm going to talk about is MediaTek extractions. This is what the extraction profile for MediaTek looks like in Detective, and it is quite a generic method. We have this list of supported chipsets. If a device has one of those chipsets, it should work. We should be able to extract the image and do the decryption. Most of the time for those chipsets that you see there, it doesn't really matter what the model of the device is or the vendor. Generally speaking, if it has one of those chipsets, there's an excellent chance that you'll be able to get the full extraction and recover the user password if it has one as well. And I said before, the methodology in this method is the physical image extraction and then hardware key extraction. There's two buttons down here for those. If you do the extract physical image extraction, it will also try to extract the hardware keys automatically as well. And this is what it looks like when you start to do the extraction. And I said I was going to go quite technical today because I really, all of these extraction methods for different chipsets, they all work in a slightly different way, but they're all quite similar. And I want to explain what some of the terminology of the different things that we see in here, and also explain why we have to do things in a certain way to get this extraction to work successfully. Because if we understand what's happening underneath the tool, when something doesn't work, I think it makes it much easier to troubleshoot things. So I'm going to talk about things like, what is this MTK-DA file that we see here? What does this disable DAA protection mean? When we go through and start to connect the device, why do we have to do all of these different things? Why do we have to turn the device off? Why do we have to use test points for some devices or button combinations? So I'm really just going to try and explain all of the different things that you see in the instructions here. But to actually start to understand the extraction process, we need to know a little bit about the MediaTek firmware update mechanism, or DFU mode, because DFU mode is how we do MediaTek and Unisoc extractions. Now, most vendors will actually have two or more DFU modes or firmware update modes on their devices. Normally, one of these is implemented by the chipset maker, and that will be implemented in the boot ROM. Now, the boot ROM, when we looked at that diagram of a chipset and there was a little bit of ROM in that chipset, that's usually where the boot ROM is held. So it's a little region of read-only memory that's contained in the chipset. And the reason that chipset makers, often put a or almost always put a DFU mode in the boot ROM is that because it is in read-only memory on the chipset, it cannot be corrupted accidentally. So, if somebody flashes the wrong firmware to their device, they will always have a mechanism or a method to put the correct firmware back onto the device, because it can't be overwritten accidentally. But there could be other DFU modes elsewhere on the device. So things like Odin mode on Samsung devices, fast boot mode, which you quite often find on things like Vivos or Xiaomi's or Motorola's or Nokia's. These are all also DFU modes, but they're held in different areas on the device, and these ones are not implemented by the chipset makers. And actually, these ones are not on the chipset. They're not in the same area as the boot ROM. So these ones can be corrupted accidentally, and sometimes that does happen when people flash the wrong firmware, which includes flashing over these other DFU modes. So the intended use of a DFU mode is really just firmware provisioning, updating that firmware to the device storage, but they quite often also provide the ability to read back the device storage. And the DFU mode that we will use in our extraction method, which is the chipset implemented MediaTek one, also has some vulnerabilities inside of it that allow us to extract things like the hardware keys, so we can do offline decryption. So a little note on the MediaTek boot process. All devices, their boot process will start with that boot ROM on the chipset. It's kind of like a BIOS or a chip with UEFI on it on a computer. But this one is read-only memory. You cannot change this one on a device. Normally, when on a device, the boot ROM, the secondary bootloader, and possibly even the third one are proprietary and written by the chipset maker. So MediaTek write the code that you find inside this boot ROM, but actually MediaTek also write the code for the second stage bootloader, which is known as the preloader. And this is quite important, and I'll explain why in a moment. The only other thing to note here is that, like I said before, this boot ROM is contained on the chipset, as indicated by the yellow. And as you go, to the second stage bootloader and onwards, these are stored on the device storage chip. So the 64, 128 gigabytes storage chip, whatever it is, depending on the device. The reason that I want to talk about the preloader a little bit is that MediaTek devices have this MediaTek DFU mode in two places sometimes, not all of the time, but usually it will always be in the boot ROM, and there will be a second DFU mode in that preloader, that second stage bootloader, and they're almost identical. They've pretty much copied and pasted the code from the boot ROM DFU mode into the preloader DFU mode. They use the same protocol, it's the same process, it's pretty much the same set of commands. And both of these can enumerate a USB COM port. So either the preloader or the boot ROM may be able to open up this USB COM port, just so that the DFU, the download firmware process can start. So they use this COM port to actually receive and run a download agent from the host machine. So if you think of your host machine as being your laptop running Detective or any other software that can communicate with these devices in DFU mode, the host machine, Detective in this case, once it establishes a connection with that DFU mode USB device, it will actually send what's called a download agent to the machine, to the device. Now, the download agent is just an executable binary. And the reason that this download agent is sent is because the boot ROM in particular is very small. The whole boot ROM is probably, maybe 50 or 70 kilobytes. Only a small section of that is dedicated to DFU mode because the boot ROM does other things. So there isn't room for much code inside there. And the download agent just has more functionality. So it's just a bigger program that is loaded into RAM. It isn't flashed to the device. It is only ever loaded into volatile memory. And it gives us more functionality. things like the ability to read and write the flash. Obviously, we're going to read the flash, and other things as well. So the key point really is that we need the boot ROM or the preloader to open up this USB port, and then we need to send that download agent, which will be executed, and then we can use that download agent connection to read back the flash. So kind of a horrible diagram here, but don't worry too much. I'm going to talk through it. And I'm just going to bring a couple of other things up on the screen. So I want to start up at the top, and I want to focus on the left-hand side of this diagram. So don't think about the right-hand side yet. So because we use the boot ROM or the preloader DFU mode to do this extraction, it does mean that the device has to be plugged off, because if the device is already in Android and fully booted, the boot ROM and the preloader have already run. We can't go back from Android to those modes. We have to switch the device off. Now, obviously, if you have a device that's in AFU mode, you should try plugging it into one of those tools that supports AFU state devices. But if those tools don't work, and in my experience for Unisoc in particular, a lot of the time they won't work, you kind of have to make a decision. Do you wait for an update to one of those tools, or do you take the risk, if you like, and turn the device off and try this method? It should work, but obviously there's always a risk for one reason or another that it may not work, and you could end up with a BFU state device. But generally speaking, this will work for devices that are in a BFU state, because we do this hardware key extraction and offline decryption. So starting up at the top with our plugged switched off device, we plug it into the host machine, which will be the laptop running Detective or Workstation. The boot ROM will be loaded and run. Now, forget about this DFU trigger for a moment, because on a lot of devices, when the boot ROM then loads and executes the preloader will open up this USB interface automatically. So I've got a note up here that says, for many devices, it is as simple as plugging the device in whilst it's switched off. And as long as the software is ready, when that preloader USB device appears, it will send a handshake. And bear in mind that this USB device only appears for 1 or 3 or maybe 5 seconds. And if it doesn't get this handshake from the software on your machine, it will just go into a charging routine and close the USB port. But if it does receive that software, it goes into a command loop, and the host sends the download agent, which is loaded and executed, and we can start to do that image extraction, the physical image extraction, and the hardware key extraction as well. Now, MediaTek is unfortunately a little bit complicated, because some of the OEMs, and they usually are the larger ones, people like Xiaomi, for example, they might remove this DFU functionality or the ability to open up this USB port from the preloader. So for these devices, we have to extract through the boot ROM. Now, we normally use a button combination, which is what I just call a DFU trigger. On some devices, it is a button combination, or on some devices, it might have to be a test point. But this trigger is really just to tell the boot ROM that it needs to open up this DFU USB port to go into DFU mode. And if you have the correct test point or button combination, and the boot ROM opens up that USB port, actually the rest of this process is exactly the same. It opens up a USB interface, it waits for the handshake, and if it gets that handshake, it goes into a command loop, and the download agent is sent and executed, and then we can extract that physical image and hardware keys. So it can be quite useful to know if you have the boot ROM or the preloader, because we do have DFU functionality in both of these different modes. Now, the vid and PID for the preloader is the standard MediaTek vendor ID, if we're talking about USB vids and PIDs, and a product ID of 2000. The boot ROM vid and PID is the MediaTek vendor ID again, but the product ID will be 0003. Now, if you've ever done MediaTek feature phone acquisitions, you will have only ever seen this device, the 003 device, because only Android devices have a preloader. Some of the OEMs do change the vid and PID. Sony is the one example that I know about where they do change the vid and PID, which is a little bit annoying, but that can happen from time to time. So what I have here is actually a screenshot from USB Log View, which is not an Oxygen tool. It's a free tool that you can download from Nersoft. I find this tool really, really useful when I'm trying to figure out if I have the preloader or the boot ROM, if I have the correct test point or the correct button combination. Because like I said before, you can use Device Manager to see what devices are appearing, but these devices will only appear for a few seconds. So you can see this one actually appeared for 6 seconds. It was probably actually a little bit less than that, and then it disappeared because it didn't get that handshake. I was just looking to see what the correct button combination or the correct test point was. But this is actually a Xiaomi device that I have, a Xiaomi Android device, and you can access the boot ROM through pressing volume down when you plug it in. So you can see that this is the boot ROM device. This is not the preloader, this is the boot ROM. So we've talked a little bit about what a download agent is, which is what's referred to in here, and Detective actually asks you to select a download agent. Different ones exist for, some of them have slightly different API functionalities or crypto-related libraries that the other ones don't have, that are specific to maybe devices or lines of devices. Unfortunately, I don't have a good list of what download agent will work for which device. The all-in-one download agent does work a lot of the time, and I would usually suggest starting there. But actually, when I talk about what is DAA protection, there are some caveats to download agents. And actually, when you combine this disabled DAA protection with this all-in-one download agent.bin, this will work for the majority of devices. But I want to talk about what actually is this disabled DAA protection option. Some devices will only execute particular download agents, and normally it's because they've been signed by an OEM. So, Motorola may sign a download agent for a particular device, or Nokia, or whoever it is, Xiaomi, etc., etc. And when you think about it, this is quite sensible. The fact that you could ever execute download agents that were not signed is kind of crazy, because the boot ROM is the first stage boot process. It has the highest level of processor enforced permissions. So if we're thinking about ARM permission levels, the boot ROM will have the highest possible level of those. So you really do have the keys to the castle. If you can execute code in a boot ROM, arbitrary code, you can do anything on a device. So it does make sense that vendors nowadays will want to sign their download agents and only allow signed download agents to run on a device. So if it is a device that requires a signed download agent, how can we find those? They may be obtainable from other sources. Sometimes these things get leaked on the internet, and that's the reason that the device extractor allows you to load a custom download agent. But actually, the easier option is probably just to use this disable DAA protection. So this option is a vulnerability and an exploit that just bypass that signature verification check. Now, this is a boot ROM level vulnerability. So if you're doing a boot ROM level extraction, this option should always work, if it's a supported chipset. And actually, if you do disable DAA protection, the standard all-in-one da.bin file will work probably 99% of the time. But because this is a boot ROM level vulnerability, it might not work if we're doing an extraction at the preloader level. Now, the software, the device extractor, will attempt to put the device back into boot ROM mode from the preloader so that it can do this DAA bypass, and most of the time that will work. But there could be some devices that verify the download agent that you might have to use the boot ROM level mode to extract through. So it all gets a little bit confusing with MediaTek, but I'm going to try and sum it up into basically 3 categories. And these are not, defined categories. This is just from my experience, what I've seen doing extractions of these devices over the years. there's usually one of three categories. So when you have one of these devices and you plug it in when it's switched off, one of three things normally happen. The first category of devices, which are probably the easiest to extract in some way, these are the ones where the preloader USB DFU mode just appears. You don't have to press any buttons, it just appears, and as long as the software is ready and waiting for that connection, the extraction will just start. These devices, if you press buttons like volume down or volume up or whatever, you won't normally see the boot ROM USB through those button presses. The second category of device, and the Xiaomi device that I have on my desk actually is an example of this. These ones you will need a DFU trigger, so you'll need button combinations to get that boot ROM USB to appear. So it could be volume down, or it could be volume up, or it could be both of them together. But these devices, if you just plug them in and you don't have the correct button combination, you won't see that preloader appear. Maybe the OEM was large enough to take that functionality out of the preloader. Perhaps some of them are actually using their own second stage bootloader. Whatever the reason may be, some devices, this preloader does not appear automatically, and it tends to be the bigger OEMs, people like Xiaomi and Vivo and et cetera. And then the third category is the hardest. So these, the preloader does not appear automatically, and the boot ROM does not appear through button combinations. So we have to use test points for category 3. So just to kind of sum this up, if we have a device in category 1, and it does need a signed download agent, we probably will be able to do it through the DAA bypass, but occasionally that might not work at the preloader level. So we might need to use test points for some of the devices in category 1. And for the devices in category 3, it will be necessary to use a test point to expose that boot ROM USB. And actually, if you think back to the device extractor, there was a line in there that said for things like Huawei, Samsung, Motorola devices, you will need to use test points. And that's because those devices all fall into category 3 that we see here. So just to talk a bit about test points, because there is a little bit of mystery around test points sometimes. But they're not as mysterious as they seem. MediaTek actually define a particular pin or pad on its chipsets to act as a DFU mode trigger, i.e. to get that boot ROM USB device to appear. Now on MediaTek devices, and you can see this inside the data sheets for MediaTek chips, it's actually known as keypad column 0, which is probably a bit of a throwback or a rewind to when MediaTek were only making feature phones that had keypads. But that pin or pad on their device acts as their chipset, and that is defined in the datasheet. And many chipset makers use a similar concept. Qualcomm have a test point dedicated for EDL mode. Unisoc have something similar. In the case of Qualcomm, we actually have to pull that pad or pin to a voltage. But with MediaTek, if we pull the test point to ground, that will trigger the boot ROM DFU mode. So how do we find these test points? We do have a library of test points in Detective, but we don't have all of the test points. We can do online research. If we just Google model test point, we'll probably find a picture of the test point. There's other things that we could do. We could backtrace from that keypad column 0, either by eye or by X-ray or by taking the chipset off. It may also be labeled as boot or even keypad column 0 on the PCB itself, or we could just guess. Sometimes I would just guess and pull various pins to ground, which if you have that USB log view tool open, you can see what devices are appearing, and sometimes you can do it by educated guessing, because sometimes you can kind of see which ones are probably test points. So these are just some test point pictures that I found online, and you can see that the first one is actually labeled as col 0. So it's not labeled as K col 0, but it is K col 0. So that is the test point. And in the second one here, it is actually labeled as kcall0. Sometimes they're labeled as boot, and a lot of the time they're not labeled at all. You can see here somebody's actually soldered a wire onto a ground point, but actually, pulling this to any of these ground points, whether it's a shield here or some of these pieces on the edge, will work as well. So one of the things I do like to talk about is, when is a test point not a test point? Because I see a lot of pictures on the internet of test points which are not really test points. Sometimes you'll see things that are not test points. They're actually connected to important eMMC or UFS pins. And I think it is important to know the difference. These are examples of a method that's known as eMMC or UFS faulting. Now, eMMC and UFS are just the chips that act as the bulk data storage on the device. And when PCB designers are designing their phone and they say, okay, I'll put a chipset here and I'll put an eMMC chip here and a microphone here, or whatever it is, they will often connect physical components like resistors or capacitors to these chips as well. And if you pull these physical components that are connected to these chips to ground, it will stop those chips from working. So if you pull a resistor that is connected to something important on that eMMC or UFS chip to ground, it will stop working. And a lot of these chipset makers will write some code into their boot ROM that causes it to go into DFU mode if it can't find the second stage bootloader, because actually the primary purpose of a boot ROM is to boot the device. So if the boot ROM isn't going into DFU mode, it's actually going to boot the device, which means it has to find that second stage bootloader. And if that second stage bootloader is on that eMMC chip, but it can't see the eMMC chip, there will probably be some logic there that says, okay, maybe there is just nothing there. Maybe I need to go into DFU mode to actually flash some firmware to the device. So it's quite normal behavior. This is just a picture of an eMMC chip to give you an idea of what these things look like. And if I go on to the next slide, there will be some, very important pins on the eMMC chip. Actually, most of them are not used, but the most important ones are the things like the data lines and data 0 for when a device is starting up, and the clock line and the command line. Those are three lines that if you interfere with them, the eMMC chip won't be able to work. So just to go on to this next slide, this looks a little bit complicated, but it really isn't. This is actually from an eMMC chip datasheet. And if you think, on the left-hand side here is this eMMC chip. On the right-hand side, the host is the chipset. In our example, this would be the MediaTek chip. When I said before that these PCB designers will follow some guidelines, these are the guidelines that they will follow. So they'll have a data sheet with things that say, for example, put a pull-up resistor on the command line, put a pull-up resistor on the data lines, put a series termination resistor on the clock lines. So quite often what you get, if we take the eMMC chip off the board and we trace from the clock line or the data line or the command line, the reason that these resistors are so close and actually connected to these important points, so this resistor is connected to data 0, this one is connected to command, is because these PCB designers have followed these guidelines. So I remember when I first started to do ISP, I was always interested by, why do we have these very convenient things that we can interface with this eMMC right next to it? And that's the reason. These are just guidelines that these phone designers have followed. So when we see something like this on the internet, which is labeled as MediaTek Vivo Y91C test point, but actually it's a little resistor, this is not a test point. This is not keypad column 0. This resistor is connected to, I don't know which one, but it will be clock, or it will be command, or it will be data 0. So pulling this to ground will have the same effect as a real test point, but it is not actually a test point. This is eMMC or UFS faulting. And it is kind of interesting that somebody has labeled this as new security, and it probably is security, because what Vivo have done is They've removed DFU functionality from the preloader. They've removed button combinations to go into boot ROM DFU mode, and they've also not put a keypad column 0 pad on the device. So the only thing that we have left is eMMC faulting as a method to get the device into DFU mode, which will normally work, but just be careful, because sometimes, especially on cheaper devices, you can knock these components off because they're not attached very well, and it's very, very difficult to get them back on. So I'm going to talk about the same kind of things, but with Unisoc, and Unisoc will be much faster because it is a little bit more simple. Again, in the Unisoc method, we have physical image extraction, we have hardware key extraction, and it's quite generic for the supported chipsets that we have here. We have some generic methods for each of these chipsets inside the tool, and it's quite a broad range of the Unisoc chipsets. The extraction is actually a little bit more simple. All that we have to do is get the device into DFU mode. We don't actually have to select download agent. All of that kind of stuff is done automatically. So once you get the device into DFU mode, you should just be able to connect it, and the extraction should just start. And it will look like this, but you can see that there's no DA mode selection or anything like that with the Unisoc method. So Unisoc, we also use the chipset DFU mode, also referred to as USB download mode in Unisoc. And this again is a proprietary DFU mode which is implemented in the boot ROM. There is no preloader equivalent with Unisoc. There actually is an equivalent of the preloader, and it does actually have the same DFU mode inside it, but I've never ever seen it be used or even exposed. I think the code is just there, but it's never ever used. So we have to use the boot ROM DFU mode to do a Unisoc extraction. So it is a little bit more simple than MediaTek. And that's the reason that this diagram looks much, much more simple. We do have to start with a switched off device again. And when we plug it in, the boot ROM will be loaded and run, and it will look for a DFU trigger. You will have to do something with Unisoc devices to get the extraction to start. I'm going to talk about what the DFU triggers are in a moment, but if it gets that DFU trigger, it will open up a USB interface and wait for a handshake. And then if it gets that handshake, it's very similar to MediaTek. It goes into a command loop. The software, the device extractor, will actually send an FDL, which stands for Flash Downloader. It's the Unisoc version of a download agent, but you don't have to worry about it. You don't have to select the correct one. All of that is just done automatically in the device extractor. If you miss the opportunity to send that handshake, you get about 20 seconds with Unisoc. It will go into a charging routine effectively. If you ever see the battery appear on the device screen, then you've gone here and you need to restart. You should never see anything appear on the screen during a successful extraction process. So what are the download mode triggers? Normally with Unisoc, very, very often volume down will be enough to get the device to go into DFU mode. It can be different. I've seen devices where it's volume up or volume up and down together, but this will work for the majority of Unisoc devices. However, there are test points as well. And actually recently we've seen Nokia start to remove the button combinations. Some of the newer Nokia Unisocs, you do actually have to use test points. And I think it's the same with some of the Motorola's as well now. So Unisoc also have this boot mode pad. And as far as I can tell, it's normally actually the UART TX pad. And if you look on a data sheet, UART TX or the UART transmit does act as a test point or a boot mode pad. So sometimes if you take a device apart, sometimes you can actually see something that's labeled as TX. There's a good chance, and it does work for this device, which is a Unisoc tablet. If you pull this to ground, so if you pull it, to maybe this or any of these shields that will be ground, that will put the device into DFU mode. Other methods do exist. Some devices, the ID pin on the USB will actually be multiplexed with the UART TX. So if you pull the ID USB pin low, which sometimes you can do through a boot cable or a boot jig, and that will work as well. And then the last resort, the same as MediaTek, you can use eMMC or UFS faulting to try and get it into DFU mode as well. So you know, the eMMC, these little resistors around it, at least one of them will probably be clock or command, or maybe data zero. So you should be able to get the device into DFU mode through one of those methods. There is a bit of a trick with Unisoc though. So if the boot ROM has received, you know, one of the correct download mode triggers, whether it's a test point or you know, volume down or whatever it may be, it's the same as doing a boot ROM extraction in MediaTek. The boot ROM will open up that USB interface and listens for a handshake, normally for about 20 seconds. Now the vid and PID of that device is 1782 and 4D00, and you can actually see this device here in USB log view. This is actually the boot ROM DFU mode. But there is a trick here, and it does confuse the process sometimes. You can see here that this is another device with the same vendor ID, the same product ID. The only thing that has changed here is the firmware revision. So if I just go back for a moment, the firmware revision as shown in USB log view is 2.02. This is actually called something slightly different in the actual USB spec. I think it's called something like BC device, but in USB log view, it's called firmware revision. But this is a device with the same vid and PID, different firmware revision, and this is actually something else. The problem is if you plug in a switched off device with no boot trigger or the wrong boot trigger, a different USB interface will be opened automatically. And it has the same vid and PID, it just has this different firmware revision, but this is not the correct mode or USB interface. This mode is actually more of an engineering mode or diagnostic mode that doesn't even exist in the boot ROM. It has no DFU functionality. It actually exists in the second stage bootloader, which is normally U-boot for Unisoc devices. The problem is that a lot of the tools will try and connect based on that vid and PID, and Oxygen actually does the same thing, and it will look like it's detected the device successfully, but the extraction will fail because this is not DFU mode. This is something different. There's two ways of telling really. You can use USB log view or any kind of USB logging tool and check this number, or if the charging screen appears at any point, then the device is actually in this mode and not in DFU mode. So if the little green battery appears on the screen, you need to start again. So I'm aware that I don't have too much time left, and I would like to leave a little bit of time at the end for questions. Once you've got your extraction, physical image extraction, so we've got the device into the correct DFU mode. If it's MediaTek, you know, if we need to, we've used the DAA signature bypass, and we've got that physical image extraction. The physical image at that point will be encrypted, because it's basically like doing dead box forensics, a dead box image. So the physical image will be encrypted. So we also need to extract some hardware keys to be able to decrypt that offline. So what do we actually mean by hardware key extraction? Often this term is used without explanation. Hardware keys are not even necessarily keys, they're more just values that are used as part of the encryption and decryption process. Now, the key thing to this is that only certain things should have access to these values. Generally speaking, on a device, probably only very early boot processors like the boot ROM or the trusted operating system will have access to these protected hardware values. So the later stage bootloaders, Android, won't have access to these values that are used to derive encryption keys. On some devices, they could be held in eFusers, which are just small regions of memory that could store important values, like cryptographic material, or it could even be, you know, IMEIs and what MAC addresses, could be other things that you might store in an eFuse. So some devices will store these hardware keys, although more hardware values in eFusers. Other devices may store them somewhere else. They may be protected areas of the eMMC, etc., etc. eFuses are just an example. A little bit about encryption. I'm not going to go too in too much detail into this. The thing to remember with encryption is that it's inherently strong. RSA, AES quite commonly used in Android. You won't brute force a good encryption key. It would take trillions of years with current technology. The trick is really, how is that encryption implemented? How do we create that good key? How do we store the things that go into creating that good key? Because encryption keys are too long to remember. This is a 128-bit encryption key. Nobody would remember that as a password, and if it was 256 bits, it would be twice as long. So we use these things called key derivation functions, and these are used for a number of things. The first thing is that you can use them to stretch a weak key. So if somebody has a 6-digit PIN as a password, we can stretch that into a good encryption key using a key derivation function. One of the other important things is that they combine multiple inputs. So where we have combination of a user password and this hardware-backed value or hardware key, like we do in Android, a key derivation function can be used to combine those two inputs, and they can also slow down brute force attempts because they can be quite computationally intensive. So the key really here is that we need this hardware key. The way that the encryption in Android works with Secure Start or with file-based encryption, it's a combination of a user-defined password and a hardware-backed key or value that goes into this key derivation function to create the encryption key that we need to decrypt the user data in the physical image that we've extracted. So we have the hardware key, and basically having that hardware key, which is the long, complicated value, allows us to guess the password, because the password will probably be quite short. You could never guess what this hardware-backed value is because it's too long, but the password is probably going to be something like a 6-digit PIN. So the important thing really is that we actually have to recreate this key derivation function. And this is quite hard. So, once we have the hardware keys, because we do offline decryption, we basically have to recreate in code, in detective, the process that the hardware key goes through in combination with the user password to actually decrypt the device. And there can be lots of different combinations of this. Different trusted operating systems that you see here, MediaTek use Kinibi, they use BeamPod, they use Tigris for Samsung, they also use Trusty. And all of these will have different key derivation function processes, and we need to understand that and implement that in software in detective. The plus point to doing offline decryption is that we can GPU accelerate it, so it will be much faster. So at this point, I actually just want to jump out of the presentation for a moment and show you an extraction and the brute force process in detective. So this is what a MediaTek extraction looks like. We have a metadata file, which is the .ewc file. We also have a keys.json, which is our hardware keys, and we also have the user data.bin. And if I pull this into detective on import, and I can enter the password here, but if I don't know the password, I can just press import. And after a moment, we should see the password recovery screen appear. So really, the last point in the presentation that I wanted to make, and I can do it whilst I'm talking here, is that sometimes people will get a successful extraction. They'll get the physical image, they'll get the hardware keys. Sometimes this decryption process inside detective might fail. Now, if it fails and the decryption doesn't work, it's probably because it's a slightly newer version of trusted operating system. The key derivation function on the device has changed slightly, and we just need to do some extra work to implement that in detective. But if we have the hardware keys, if we have the physical image, we will be able to implement the new key derivation function within detective, and we do that quite regularly for people. So this is the password recovery screen. We can choose the different types of attacks we want to run, 5-digit, 6-digit pins, password patterns, dictionaries, etc., or we can create custom attacks. And if I hit start password recovery, it will be very, very fast. Unfortunately, this is a MediaTek Xiaomi device. You won't really see the attempts go up because it's only a 4-digit pin. with GPU acceleration, you're talking, 5, 10, 15,000 attempts per second. So you can see down here in the bottom right, it's found the user data pin code that protects the data, and then it is able to extract the decrypted data and decrypt it offline. So the decryption is done offline in Detective. You do not need the device once you've done the extraction. As long as you have the hardware keys and the physical image, you don't need the device once you have that extraction. The decryption happens actually in the software. This is just the password manager and the password attack builder, where you can build things like the join attacks, etc., etc. Really, really important if you do have an alphanumeric password. 6-digit pin. If you're brute forcing at 5 or 10,000 attempts per second, you're gonna recover that within a few seconds. But if it is, a complex alphanumeric password, even with offline GPU accelerated password recovery, you will probably still need a clever password attack. And this is just what I was talking about. If it's a supported chipset and the decryption doesn't work, most of the time we will make it work. And I do see customers that have active support and maintenance subscription. We do get a lot of requests to say, oh, this device, the decryption didn't work, and we're normally able to add support quite quickly, because if it's just a different version of the trusted operating system to what we've seen before, we just need to do a little bit of reverse engineering to make the decryption possible. So I appreciate that was not very much in the tool, a little bit more technical, and some of the underlying theory. A lot of what I've talked about will actually be relevant to other tools as well. So I always just try and maybe teach people a little bit about the underlying process and the underlying theory, as well as talking about some of the stuff that you can do within Detective. So I just want to say thank you for listening, really. And if there are any questions, please feel free to put them in the chat. I will probably